Hello everybody and welcome to this webinar on the art of measuring at the nanoscale, and our topic will be mastering quantitative atomic resolution with scanning transmission electron microscopy. This is the first part of this webinar. I'm Dimitrakopulos. I'm the coordinator of the Nanoscopy-Gr network of laboratories, and I come from the nanostructure materials microscopy group of the electron microscopy laboratory of the School of Physics in the Aristotle University of Thessaloniki. First, let me say a few things about this Nanoscopy-Gr network, which is a collaboration between our lab and the corresponding lab of the Research Center Demokritos, and also the University of Oslo and the corresponding network of laboratories of Norway that is called HRTEM. The aim of this Nanoscopy-Gr network is to strengthen our collaboration and networking and exchange of knowledge, and to try to develop an integrated methodology of nanoscopy and modeling for studying nanomaterials down to the atomic scale, and with this methodology to be able to tackle the challenges of today regarding the nanoscopic characterization of materials and devices. And at the same time, we want to do what we are doing today, in other words, to educate and inform researchers and young people on what electron nanoscopy can do. I would like to start with acknowledging my collaborators, which you can see here in our group and our collaborating groups. And this is the site of our laboratory, and also you can find us in the booking platform of the Aristotle University, where you can book your time in our instruments, and also in the Innovation EL nanotechnology infrastructure of Greece, where you can, if you're not from the Aristotle University, then you can book your time using this platform. Recently, our lab has lost a very valuable member. Professor Emeritus John Stoimenos passed away, unfortunately, and so we would like to dedicate this event to his memory. A concept that is very important today is that of nanometrology, and because it's essential to be able to measure the nanoscale in order to be able to control quantum phenomena and deviations from the macroscale behavior, and to authenticate nanomaterials and devices. And the goal here is to develop measurement techniques that can achieve quantitative chemical and structural characterization of nanomaterials with high resolution and accuracy. And such a technique is quantitative high-resolution scanning, transmission, electron microscopy, as also transmission electron microscopy, which both techniques offer atomic resolution for direct determination of composition and strain. So in this way, we can address the unique physical and chemical properties of low-dimensional materials, whether they are zero-dimensional like quantum dots or nanoparticles, one-dimensional like nanowires, or two-dimensional like thin sheets, for example, graphene, and two-dimensional semiconductors. And regarding two-dimensional heterostructures, the ultimate limit, of course, is the single atomic monolayer. So we want to be able to correlate the structure and the composition to the properties of the materials. And the quantitative high-resolution TEM or high-resolution scanning TEM can allow us a direct determination of the structure and composition. In other words, we can directly visualize and measure the structure and the composition. So, especially regarding high-resolution scanning transmission electron microscopy, it is possible to see the structure, measure the deviations of the atomic positions from the equilibrium positions, in other words, measure the strain field, and at the same time you can also use the chemical contrast, like you see here, to differentiate the chemical composition and measure quantitatively the chemical composition, and you can do this down to the atomic scale. Well, for that purpose, you need high-angle annular dark field STEM, which is chemically sensitive. So the image intensity depends both on the average Z number of the atomic number of the projected atomic columns. This is why it's called Z contrast, but it also depends on the thickness of the TM sample. And today, with the new aberration correctors, we can visualize the atomic positions, the atomic columns, either with high resolution TM or high resolution STM with picometer precision. So this is the outline of this seminar. First, we discuss a little bit about our integrated approach, and we give some elements regarding the topological analysis of structural defects and interfaces, and then we go into the quantitative high-resolution STEM for measuring composition and strain, and how we can utilize positional determination with high accuracy for strain and defect analysis, how we can measure nanoscale strain fields by finite element analysis, and do quantitative compositional analysis by high resolution STM. So this is our integrated approach. In other words, starting from the experimental observations, we try to obtain the atomic scale composition and the strain at the nanoscale. And to do this, we at first stage perform topological, in other words, crystallographic analysis, and also elasticity theory, as well as possibly image simulations. And all this information is combined with modeling by ab initio or large-scale energetic calculations, for example, by molecular dynamics. And there is an interaction between experiment and theory in order to arrive finally at the accurate structural and chemical model, as well as the strain composition coupling, and to correlate this with the physical properties. Regarding topological analysis, which is primarily performed for defect characterization, this is based on Curie's principle on symmetry compensation, according to which the information that is related to the symmetry of the material is never destroyed, but in fact symmetries that appear broken manifest themselves in defects. So this very important conservation of symmetry principle was later applied and developed for bicrystals by Robert Pont from the Liverpool University, and then it was more generalized to more general structural compensation by myself and Pont. So this is a theory that can be employed for a priori characterization of defects. In other words, suppressed symmetry gives rise to defects, and also structural operations within the unit cell may give rise to defects. And then we can have a knowledge beforehand of the geometrically admissible defects in a material. And here is an example of a recent application of this theory regarding closed domains that are formed by the overlap of stacking faults in gallium nitride. And depending on the sense of the overlapped stacking fault structural units, you can have a closed domain that is defect-free, or you can have a domain that is surrounded by a partial dislocation loop that is very similar to Shockley partial dislocations. And another thing that you can do with this topological theory is that you can do also a posteriori characterization. This is the well-known Burger circuit for isolated dislocations, but Pond and co-workers have generalized this to circuit mapping using symmetry or structural operations. Such operations can be, for example, rotational operations or mirror operations. And so now you can use circuit mapping not only around isolated defects, but also around defects that are on interfaces, or defects that bound stacking faults, for example, and generally all sorts of defects. And it's also a nice way that you can confirm the prediction of geometrically necessary defects, but this time using experimental images. So now let me go into more detail on the subject that we are dealing today, which is quantitative high-resolution STEM for measuring composition and strain. So we have developed a roadmap for comparing experimental observations to structural models, and here is an example using these ultra-thin quantum wells of just one monolayer of indium gallium nitride inside gallium nitride. So you get the experimental observations from which you can obtain the nanoscale strain map based on the positions of the projected atomic columns, and also you can obtain the intensity of the atomic columns. And then you go to compare with simulated models that you have obtained either with ab initio or empirical potential calculations. And for this purpose, what you need is image simulation. So you perform image simulation of the calculated models, and in this way you can compare the image simulations, as will be explained in detail later, to the experimental observations, and then deduce quantitatively what is the, for example, the amount of indium in this monolayer that you are observing. What we do is that we ask the computer to identify the positions. It's doing some kind of fitting. Isaac will tell you more about this. It's fitting a two-dimensional Gaussian on its atomic position. Then it divides the space. It causes, it makes a tessellation, as we know, or as we call it. It's called Voronoi segmentation, and then calculates the intensity within its Voronoi cell. Also, in order to be able to do such quantification, you need to be able to ask the computer to make a classification of the peaks into sublattices, because maybe your material is not a single lattice, like a simple, let us say, FCC structure. It may be a more complicated structure like this, which is hexagonal. And in hexagonal close-packed structure, we have two interpenetrating sublattices, the A sublattice and the B sublattice. So the computer must be able to know the sublattices. So it must be able to define the nearest neighbor positions for each atomic column. And also we have the other approach, which is geometrical phase analysis, which actually is a method that works in Fourier space. Nowadays, geometrical phase analysis is very well known and used. So I will not go into real detail here. It was developed by Martin Eitz, and you can find it commercially, or you can find it free in many tools around the internet. There's a whole community of people that are working on computer methods for electron microscopy. Just to say, for the sake of completeness, that both with peak finding and with geometrical phase analysis, what we want to find is the displacement field. So this is the displacement field. Of course, we are talking about images. Images are two-dimensional projections of the three-dimensional crystal. So you can find the two-dimensional projection of the displacement field. This means that the deviations of the atoms from their normal position. For example, if you have a material that changes its structure, like here you have gallium arsenide, and then you have indium gallium arsenide, and then back to gallium arsenide, the lattice periodicity is going to change. So when you want to identify this change in the lattice periodicity, you identify it through the displacement field in this particular region of the indium gallium arsenide. And from this, of course, you can get then the strain field by differentiating, taking the first derivative of the displacement field. Now, what is done in geometrical phase analysis is that it works in Fourier space. So by making the Fourier transformation similar to taking the diffraction pattern, let us say, it can differentiate the changes in position of the, let me call it, spatial frequencies. So an experimentalist will call it diffracted beams. So the changes in the spatial frequencies and the intensity in real space is made by the Fourier transform, the inverse Fourier transform of these spatial frequencies. And each spatial frequency depends, has an amplitude and has a phase. And the phase depends on the displacement field. So by calculating the phase for two positions, you can obtain the displacement field, which is what we want. So this is how GPA works, and we are not going to discuss it any further. So these are some results from GPA. With GPA, you can either characterize distributed strain fields, long-range strain fields, or localized strain fields. Like localized strain fields are the defects, of course, the dislocations. So you can do both. If you are working with distributed strain fields, then you can find the strained lattice parameters in a place where the lattice changes. And then, if you know your elastic state, how the material deforms, you can deduce the relaxed lattice parameters. And for example, if you have a binary alloy, you can find the chemical composition by using Weger's law. So this is an indirect way to find the chemical composition. We have, let us say, a reference lattice, like here gallium nitride. This lattice changes. For example, here it becomes aluminum nitride. So what you do is that you map this change with respect to the reference area, which is gallium nitride. So you can measure, having as reference, your gallium nitride. And then you find how much your lattice parameters change, and by this measurement of the lattice parameters, you can determine the composition that corresponds to these lattice parameters. So this is a structural way of determining the change in the composition. Of course, you can do exactly the same thing with peak finding. Peak finding is not working in Fourier space, in the inverse space, reciprocal space. It's working in direct space. But it's doing exactly the same thing. It's measuring the positions of the atomic columns, and you can measure it with respect to some reference area. So you can again deduce the strain field in exactly the same way, but the additional advantage of peak finding for high resolution STEM is that you can also deduce the intensity of the atomic columns, and if you know what you're doing, you can deduce the composition. So you can correlate and you can check if your strain determination agrees with your compositional determination. Of course, this is not a very easy job. It's not straightforward to do it. Now, if you want to be very accurate in determining position, let me start first with position, and I will go to composition later. Then you have to use optimized imaging conditions. Everybody knows in microscopy about the Serger defocus. There are also other imaging conditions. One cannot say which one is the better. The better one is the one that's doing your job. Of course, nowadays we have the aberration corrected, so the spherical aberration is 0, and so you can use 0 spherical aberration, or you can use negative spherical aberration conditions, which under some circumstances you can use it, for example, to show the light atoms like nitrogen in gallium nitride, which is not straightforward to see the light atoms in aberration corrected microscopy. So we have used such conditions. In fact, first we have to do the hard work, which means that we have to do image simulations. In our community, if you want to do image simulations for transmission electron microscopy, not scanning transmission, just transmission electron microscopy, you use the GEMS software, and you can find with which conditions, for example, you can see if you have a binary compound like gallium nitride, you can see the gallium columns brighter, or the nitrogen columns brighter, or both columns with about the same brightness. You see here the thickness of this depends on the thickness of the sample. When I'm saying the thickness, I mean the foil, the TM foil that you are using in the microscope. So this has certain, let us say, constraints to be used properly. But in a recent work we have used it, and I'm glad that Yulita Smolk is in the audience, who took this image, this beautiful image with these conditions, and we were able to directly make a correspondence between the structural model of a dislocation and the experimental image. So this is a nice way to do a direct visualization, especially for the core structures of defects. You see that we go with very high atomic resolution, and you identify the core structures of defects. Now, regarding strain fields in general, I told you earlier that you can use, instead of atomistic calculations, you can use also finite element analysis. You can indeed employ such an approach, which is a continuum approach. It's not atomistic approach, but we have shown that it works very nicely at the nanoscale, and we have used it for quantum dots and for nanowires, for example, and we were able, with the finite element analysis, to quantify the strain fields that we were observing. So this is also an example from cross sections of core cell nanowires, and this kind of analysis gives you the additional advantage that you can use Cartesian coordinates, or you can use cylindrical coordinates. Here, this is in cylindrical coordinates, and you can use you can see very nice images of the strain field, like kaleidoscopic images of strain fields. And you can be quantitative with very high accuracy. So now I would like to go in a little bit more detail about compositional analysis with high resolution STEM. One thing that is a must that we must start with is that we need to do intensity normalization. And for this purpose, you need to take into account the sensitivity of your detector, of your high angle angular dark field detector. So first you start with this step. This has been very well known and developed by people like Rosenauer and others before him. Another thing that we need to do is noise reduction. And high resolution STEM images are, by nature, they are quite noisy. Even if they are obtained with probe corrected microscopes. So there are ways to do noise reduction. Mainly, you have to do it without tampering with the actual intensity that you are recording. You have to be very careful on how to do noise reduction. And one way that is very commonly used is the overlapping of multiple images. You also need to know the thickness of your sample, which Isaac will tell you a bit more about, and also you need to know the source size, the size of your probe, so you can use image simulations and compare the column the atomic column that you are observing. So you have to do you have to scan your atomic column along various directions and obtain the Gaussian. And from the full width half maximum of the Gaussian, you can define the source size. And you need this in order to be able to choose the appropriate image simulation that you are going to use. So if you have all this information, what you do is you do intensity measurements. Of course, we are showing this in a rough way, because in reality, you are using the Voronoi tessellation of your image. You have separated your image in Voronoi cells. So you are taking the intensity, say, of multiple such cells. And if you say you have an area where you have different intensity, then you need to compare it with a reference area where you know the composition. For example, here is gallium nitride, and this is a quantum well, a very thin one, which is indium gallium nitride. So you measure the ratio, how much more bright is this area compared to the reference area. So you make a column intensity ratio. But you have to keep in mind that it's not a straightforward thing to correlate this intensity ratio to the composition. You need to do the hard work. You need to do image simulations, because this intensity ratio, even for a certain composition, is not stable, but it changes with the thickness of the TM foil. So you see here that this is for
100% indium nitride, and outside we have gallium nitride. So this is a pure binary in this simulation. So you see that for very small thicknesses of the sample of the TM foil, there are very large variations. And then if you go beyond, let us say, 40 nanometers thickness, then we have a linear relation that we can trust. And of course, there are also variations due to the source size. So simulation is a must if you want to be quantitative. Image simulation based on proper structural models. How do you do image simulation? There are a couple of approaches. One is the Bloch wave, but the more common one is the multi-slice image simulation. So you consider your crystal to be composed of many slices, and each slice you take it to be like a weak phase object. So it's all in the books. So I'm not going into any detail on this one, but for STEM, you need to take into account also the thermal diffuse scattering. In other words, the atoms are moving. And in order to be able to take into account this thermal vibration of the atoms, we use what is called a frozen phonon approximation. In other words, we make different, let us say, photos of the material in different phonon states, different vibrational states. We use the Einstein model of uncorrelated vibrations. And then if you calculate, let us say, 10 phonons or more, then you are quite accurate and you can do the overlap of these 10 phonon calculations and get your structural, your simulated model. Of course, in order to do this, you need to have, again, the energetically relaxed atomistic supercells, because these supercells, like this one, they will give you what is known the static atomic displacements because of the strain, because of defects, interfaces. Atoms may be deviated from their normal positions. Also, the strain, yes, the strain deviates the atoms from their normal positions. So it separates the atomic columns and changes their intensity. And also the chemical environment changes the intensity of the atomic columns. So you need to have the appropriate, let us say, empirical potential. For example, if you are using molecular dynamics in order to have an accurate model. If your structural model is not accurate, then your quantification will not be accurate. So I think I'm going to stop here and take your questions before passing over my role to Isaac.